Now we're going to talk about orbits and gravitational force, specifically Newton's law of universal gravitation, which is this equation right here. So far in our discussions about gravitational force, you guys have seen the equation Fg is equal to your mass times little g. Well, that works if you know what the gravitational field strength is. But how do we know what that is? Well, if you notice, if I combine all of this stuff together, this is going to be the same as what your G is. And M2 is going to be the mass of you, or the mass of the object that is interacting with your planet. This equation, the Newton's law of universal gravitation, works all the time with any two objects. So I could find the gravitational force between me and my dog. I would just need to use this constant. So this capital G here is the universal gravitational constant. So this is always 6.67 times 10 to the negative 11 meters cubed over kilograms seconds squared. And so that's always there. And that constant is on your equation sheet. And then for the mass of each object, this is would be the mass of me, and then this could be the mass of my dog. If I was trying to find the gravitational force between myself and the Earth, then it would be the mass of me and the mass of the Earth. And it doesn't matter which one is M1 and M2, because if I do 3 times 2, that's the same as 2 times 3. So the order does not matter. You just need to know that you need to put both masses in there when you're multiplying everything together. And this R squared is the distance from the center of one object to the center of the other. And it's weird at first that this is R, but it actually makes sense, because if I'm talking about here's the Earth, and I am standing on the Earth. Here I am standing on the Earth. And relatively speaking, I'm even smaller than that. I am not that big compared to how big the Earth is. So if I want to measure from the center of me to the center of the Earth, if you look at this, that's basically the same as the radius of the Earth. And if I want to talk about an atom, here's the nucleus of an atom, and here's electrons going around the atom. Out here might be some electron, and I could talk about the attraction between the nucleus and the atom. Well, this will be essentially the radius of the atom. And then we also have planets. So if I have the solar system here, and this is my sun, I can have planets going around it. And again, it would be the distance from the sun to the planet, which is basically the radius of the orbit. All right, so when we're talking about orbits and gravitational force, then now you know why it's an R. And this G is the same as all of this stuff. So if I take a look at this, the G is a constant, so 6.67 times 10 to the negative 11. And then if I have the mass of the Earth, which is 5.972 times 10 to the 24, and I divide that by the radius of the Earth squared, and I divide that by the radius of the Earth squared, which is 6,371,000 meters, and I multiply all that together and divide it, I get 9.8. Which is why we use the little g, because the radius of the Earth isn't changing, the constant isn't changing, and the mass of the Earth is not changing. So if I already know what all that stuff is equal to, and it's 9.8, then all I need to do is worry about the mass of me and this magical g that is 9.8. So we're going to do another example. For a carbon atom, the radius of a carbon atom is 70 picometers. 70 picometers is the same as 7 times 10 to the negative 11 meters. The mass of a proton is 1.67 times 10 to the negative 27 kilograms. The mass of an electron is 9.11 times 10 to the negative 31 kilograms. And I want to assume for a moment that the force between the nucleus and the electron is 9.4 times 10 to the negative 11. And later on in the year, you will learn how to get that number. But for the moment, I want to know how fast is the electron going. All right, so if I look at an electron being attracted to the center of my atom, that is going to be my electrostatic force, which in this case is 9.4 times 10 to the negative 8. And so this would be as it's going around the circle. So I could also draw it up here and being attracted straight down. That would also be fine. So the sum of my forces is only the electrostatic force. Its mass is so small that we can ignore gravitational force. Plus, I'm just focusing on the force between the electron and the nucleus. So we have our electrostatic force is going to be equal to our mass times the acceleration to go in a circle. The electrostatic force that we were given is 9.4 times 10 to the negative 8. I want to know the force on the electron because the electron is what's going around. So I need to use the mass of the electron because that's the thing flying around in a circle. So that is 9.11 times 10 to the negative 31. And then the acceleration to go in a circle. We don't know what that is, but we do know that it's v squared over r. So now I'm going to plug in the values for my velocity and for my radius. So the radius that we're given is 70 picometers. So that's 7.0 times 10 to the negative 11. And then for velocity, we need to remember that velocity is equal to our change in position over change in time. But all we're trying to solve for here is velocity, so I'm not going to care about that. I'm just going to put in v squared. And then I just need to solve it. So I'm going to multiply both sides by 7 times 10 to the negative 11 and divide both sides by the 9.11 times 10 to the negative 31 to get v squared by itself. So once you get that, then you have 7.22 times 10 to the 12 is equal to v squared. So I'm going to square root both sides. And I get 2.69 times 10 to the 6 meters per second. So it is going really, really fast. And the last example that I want to go over is satellites. So with a satellite going around Earth, there are some geosynchronous satellites. A geosynchronous satellite is where if you look up right now, right there in the sky, there's a satellite. And all day, every day, it doesn't look like it moves at all. Well, in reality, since the Earth is rotating once every day, that means that that satellite has to go around Earth also once a day, exactly once a day. So that is what geosynchronous means. A geosynchronous orbit is when a satellite seems to stay in the same spot in the sky relative to someone on Earth. This means that every day the satellite must orbit the Earth exactly once. This is really handy for satellite TV because with satellite TV, you want to take your satellite dish, aim it at one spot in the sky, and just leave it there. You don't want to have to turn it every couple of hours so that you can still get your TV station. You want to aim it at the satellite and not have it move. The second question is, how high above the surface of the Earth does a geosynchronous satellite need to be? So we're going to start with a force diagram. The only force that's being applied is our gravitational force, and we need to use our new fancy equation. So Fg is equal to G times the mass 1 times mass 2 over r squared. And for the net force equation, we have just Fg is equal to the mass times the acceleration to go in a circle. So for our gravitational force, G is a constant. We'll leave that there. Mass 1 is going to be the mass of the Earth. Mass 2 is the mass of our satellite divided by r squared. And that's going to be the distance from the center of the Earth to the center of our satellite. So that is going to be this distance here. Okay, so this distance is r. Okay, so the r goes from the center of the Earth to the center of the satellite. And that'll be equal to the mass of the satellite times v squared over r. And again, that r is from the center of the circle, which in this case is the center of the Earth, to the center of the satellite. So both of those r's are the same r. All right, so now I can work on solving this. The first thing I'm going to notice is that I have an r on both sides, so I can cancel out one of these r's with one of those r's. So I have g times the mass of the Earth times the mass of the satellite over r is equal to the mass of the satellite times v squared. The next thing that you guys might notice is that I have the mass of the satellite on both sides, so that can cancel out. All I have to do is divide both sides by the mass of the satellite. So now I have g times the mass of the Earth over the radius from the center of the Earth to where the satellite is equal to v squared. So the next thing I need to recognize is this velocity bit. And remember that velocity is equal to your change in position over your change in time, which is what's important for a geosynchronous satellite. So it needs to go once around the Earth, which is the circumference, which is 2 pi r. So 2 pi times r over the amount of time that takes. And the time that takes is 24 hours. So let's figure out how much time that is in seconds. So 24 hours. I know that each hour, so 1 hour is the same as 60 minutes. So my units of hours cancel out. And then I know that in every minute there is 60 seconds, so 1 minute. And I know to put minutes on the bottom because I need the units to cancel out. So if I have minutes on the top, then I need minutes on the bottom to cancel out. So how many seconds does it take to go around? So 86,400 seconds for it to go around once. So I'm going to stick that down here for my time. So I get G times the mass of Earth over R is equal to, and the most important thing here is I need to remember not to forget to square that velocity. So I'm going to have 2 pi r over the 86,400, and that's going to need to get squared because velocity is squared. Now, because the whole thing is squared, I can square both the top and the bottom separately, which should make things look a little less scary. And I'm going to just multiply this out, and I'm going to put all the numbers in. So I'm going to multiply both sides by r. So this r cancels out there. And then I'm going to multiply. All right, so when I get 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24, and then multiply it by the 7464960,000, I get 2.9725 times 10 to the 24th. So then I need to divide both sides by the 2 pi squared. So when I divide by 2 pi squared, that cancels out. And I get 7.53 times 10 to the 22 will be equal to r cubed. So then to do the opposite of cubed, I need to put everything to the 1/3 because the opposite of cubed is 1/3. Because if you remember, your exponents multiply. So if I want 3 times something to equal 1, I need to do 1/3. So I do the cube root of this. And I get 4.22 times 10 to the 7 meters is equal to r. Now, if remember, here's my Earth and my satellites up here. And so this r is from the center of the Earth to the center of the satellite. So that distance is this r. So I wanted to know in this question, how far is it from the surface of the Earth to the satellite? And we're going to call that d. Well, if I know the radius of the Earth, which is, how about we'll call it RE, then the radius of my Earth plus d needs to be equal to this r that I just got. And the radius of the Earth was given as 6,378 kilometers, which is 3.78 times 10 to the 6 meters. So I subtract the 6,378,000 from both sides, and I get a distance above the surface of the Earth of 3.58 times 10 to the 7 meters. And that is our answer. If you have any questions or problems, let me know. And this question in particular, the hardest part is making sure you plug all the numbers into your calculator right. Even I did it wrong a couple times. So if you do it wrong, you're not alone. Good luck, and let me know if you need help.